apologize for the lack of that, not being that present. So, what we have, this is a redox reaction. So we need to talk about the reduction of water and the oxidation of water. Two completely different things. So, if you look on your chart, find the equation for the reduction of water as it is written on that chart.
2
What do you got?
2 water.
plus 2 electrons.
Plus what?
2 electrons.
Turning into
Hydrogen gas and 2 hydroxides.
and 2 hydroxide. Okay? Cool. Now, that's the reduction of water. What's that value?
Negative 0.83.
Negative 0.83 volts. Okay? So that's for the reduction of water, going in the direction that it's written. Now, we need to talk about the oxidation of water. The oxidation of water is not the reverse of this. The oxidation of water is where you're going to find on that chart water over here on the product side that's going to get flipped. Okay? So find where you have water as a product, and you're going to have, let me give you a hint, you're going to have oxygen as a product. So you're going to have water as the reactant, you're going to have oxygen as a product. What do you get out of that?
O2.
So you're going to start with the water.
Oh, you want to two waters.
2 waters.
Oxygen gas. 4 hydrogens, or 4 hydroniums, and 4 electrons.
And 4 electrons. And what's that value? Once you flip it.
Negative 1.23.
Negative 1.23.
Double negative.
Oh, double negatives, right? So, what I want to do, so here's my reduction equation, here's my oxidation equation. So here's my 2 half reactions. So what I need to do is add these together, okay? So I get things to cancel out.
Double the top.
So, I got 2 electrons up here, so what am I going to have to do?
Double the top.
Double that. So I'm going to have to multiply everything here by 2. So that gets me 4 H2O, 4 electrons, 2 H2, and 4 hydroxide. Cool. Now, I'm going to add all this together. So over here, I've got a total of 6 waters. My electrons are going to cancel out, okay? So what I've got left with, then over here, I've got H2, I've got O2. Now, here's the cool thing. What do you think you're going to get when that hydroxide hooks up with those hydronium ions? Water. Ah, I'm going to get total of 4 water. So I've got,
Oh yeah.
right? So this is going to go away. So what I'm going to end up with, because I've got 4 over there and 6 over there, I'm going to end up with a total of 2. So we got 2 waters yielding 2H2 plus O2. Now, this is what I said is supposed to happen. So here's what you've got on where that, and it's the same thing. Reduction occurs at the cathode or anode.
Cathode.
Same idea. Reduction occurs at the cathode. Oxidation occurs at the anode. So what you saw and what's going on, I have no idea. I've done this literally for decades. What happened? I don't know. We'll figure that out later. But here's what's important. Where you had the reduction of water, you were producing hydroxide ions, right? And that production of those hydroxide ions is what was turning that solution a magenta color. So that if you just put those in, you're going, wow, and all you have is pure water. And you're trying to figure out which one is the anode, which one is the cathode. You know, when you look at these reactions, when you're producing hydroxide ions, that's associated with the reduction of water. Now, here's the other thing that's going to happen. Notice that you're producing 2 hydrogens for every 1 oxygen. So when you do this reaction, that's the other way that you can figure out which one is the anode, which one's the cathode. The hydrogen, you're going to get a lot more bubbles because of the fact that you're producing 2 moles of hydrogen to every 1 mole of oxygen. Now, is this reaction spontaneous? How do you know?
Double negative there.
No. Just how do you know that that reaction is not spontaneous?
We're like,
We had to use electricity.
we're alive.
Because then we
Yeah.
die.
We don't
We
have
die.
Water is stable. If this was a spontaneous reaction,
The ocean
Okay.
would turn to hell.
Yeah. He's right.
Hey, just think about it. The oceans would turn because the hydrogen would blow up. See,
But here's
just
the point.
2 steps behind.
if this was a spontaneous reaction, we would not have oceans because what would the water automatically turn into? Hydrogen and oxygen. So this, basically what we're saying, and we'll talk more about this later when we get into thermodynamics. So water is stable. So if you think of this as being like a roller coaster, water's down here at the bottom of the roller coaster. When I put that electricity in there, I'm forcing it to go in a direction that it doesn't want to go. And then I produce hydrogen and oxygen. So that's like at the top of the hill. Now, for those of you, I know if you have seen a hydrogen balloon explode, right? Okay? So if I've got these 2 up here as hydrogen and oxygen, and I throw a match into it, what happens?
Boom.
Boom. So that's like rolling down the roller coaster. And the chihuahuas go, whee! Okay? And they yell and they scream and they emit light, and it's a grand thing. But here's the story. The reason that I have to have this is because of the fact that it doesn't want to go in that opposite direction. So this is providing the energy to separate that hydrogen and oxygen. Okay, next one. We'll see if the chemistry works any better on this.
You can't go over 2.
If it doesn't, I'm just
He's gonna quit.
No, I'm just kidding. Oh, yeah, that's it. I'm just going to walk out. I'm done.
One day,
Somebody else can fill in the rest of the year. I'm
one
just
day without Michael.
okay.
Yeah.
Now,
David.
so the next one, I'm going to have a solution of potassium iodide. So, is potassium iodide soluble?
Yes.
Very much so. So here's what's going to be important. I've got this solution of potassium iodide. How are these actually existing?
A plus, I minus.
So I've got 3 things in here. I have potassium ions. What else you got?
I minus.
I minus, and what else you got? One other big thing.
Water.
Water! You got water.
You got that? That's ice.
Okay, that's it. So what that means is the only thing that I can have listen to me very carefully, the only thing I can have as reactants are potassium ions, iodide ions, and water. That's it. I don't have potassium, I don't have iodine, I don't have hydrogen, I don't have oxygen. This is it. These are the only things I could potentially have as reactants, because that's all I got in here, these 3 things. So let's talk about this. So let's talk about what could possibly go through the oxidation process, could potentially go through the oxidation process. So could potassium, I'm just saying it's not going to happen, I'm just saying could it happen? If potassium got oxidized, what would that turn into?
K2.
You would lose an electron and it would turn into K2 plus a chihuahua. Ever see K2 plus?
Oh,
No. Could happen?
probably not.
No. Possibility. What about the iodine?
Definitely. Elemental.
So that will turn into I2 plus 2 electrons. Bounce that, put that. Now, listen to me very carefully. The way this is written is this on your sheet going in this direction.
No, oxidation.
It's oxidation. Okay. So once this gets oxidized, okay, what's the value of E naught? Once you flip it.
Negative 0.53.
Negative
53.
0.53. Okay. Could water undergo oxidation? Good. We just did this over here, right? So the oxidation of water is 2H2O, yielding O2 plus 4 hydroniums plus 4 electrons. Now, this not going to happen. Not a chance. Not a chance. If this was happening, anybody happen to know the color of iodine?
Brown.
Brown, right? Brown. So if this happened, you would see iodine actually forming. How could you check if this was happening? What's two things would you see happening?
Bubbles.
You'd see bubbles of oxygen gas. Well, what would happen to the pH of the solution?
Down.
pH would go down because you're generating hydronium ion. So if this happens, I'll see it. I'm producing iodine. This happens, I'd see a gas and I'd see the pH go down. Cool. Now, would these be happening at the cathode or at the anode?
Anode.
Why?
And ox.
Okay, so if this is happening, that would be happening at the anode. Cool. All right? Now, what's this value for the oxidation of water? What's that E naught value?
Negative 123.
Negative 123. Okay? All right. Now, on the reduction side, what could potentially get reduced?
K plus.
Yep.
K plus. You could make K plus, take in an electron, and turn into elemental potassium. You could do this. But how do you know that's not happening? Because if you made the potassium, what would it automatically do?
React with the water.
You always see potassium react with water. What does it do?
Boom.
It goes boom. So even if you made the potassium, even if you made it, it would automatically, instantaneously react back with the water and go back to the potassium ion. Like, hey, you can make me do it, but I'm not happy, and I'm going to go back to this form.
Is
Now,
potassium metal the one you can cut with a knife? Like it's super.
same thing with sodium, same with lithium, all your group 1 elements. Now, here's what's important. Nathan Nelson, what's the E naught value for this reaction the way that it's written? Way down at the bottom.
Oh, K plus in an electron, elemental K, negative 2.92.
Negative 2.92. Big negative number. Does Mother Nature want to go in this direction?
No.
Okay, so that's reduction. Could iodine take in an electron?
I mean, I guess technically.
Technically it could. What would you make?
I-2.
I2 minus. Ever see I2 minus?
Not really.
Nope. That's not going to happen. So what do we have left? The reduction of water. So the reduction of water, okay, is going to be, in this case, 2H2O plus 2 electrons, turning into H2 plus hydroxide, right?
Yes.
So if this happens again, what are you going to see?
Gas.
You're
Base.
going to see hydrogen bubbles and
Base.
bases. Okay, so now, let's see if, what's on this one.
Nathan must be.
Okay. So, here's my potassium iodide. Put the little element free don't rise. We'll try it first without any indicator in there. Please, Lord. Please, Lord. Please, Lord. Okay?
Reddit.
So, over on one side, I got bubbles forming on one, okay? And the other one is kind of getting this reddish brown,
Can you flip the tape around?
Iodine.
huh?
Can you flip the tape around?
You want to see what's going on?
Miss Morgan, do you want me to bring the
Iodine.
camera closer to show the camera?
Oh, we can see that.
Ooh.
Someone get the flame.
Okay?
Oh wow.
All right?
Wow.
Wow.
Oh, wow.
Okay? So, if you can, that one finally worked. Yay. With the broken science. So, one side they're producing lots of bubbles, and the other one was turning
Brown.
brownish. Okay? So, what are the 2.5 reactions that are taking place are this one and the water. So when I add those together, okay? So I've got 2 iodines turning into I2. And I can tell this because of the fact that I'm producing iodine. I got water. So conveniently, that's 2 electrons. Conveniently, that's 2 electrons. Don't have to worry about that. So I've got 2 H2O plus the iodine, and I'm producing iodine and 2 hydroxide. Okay? So here's the story. If you look at this, what you have on this side, and this is where the wheels fall off. What you have here can only be what's in the beaker. Okay? That's it. I can only have what's in the beaker. If you try and put like hydrogen gas and iodine over here, you can't do it. Why can't you have these as reactants?
It's not in there originally.
They're not in there. The only thing you have are this. So when you get done with these reactions, this is why it's so important that you start with what you have in the beaker. All right,
K plus is a plus.
last one. I got silver nitrate. Smash that. Last one, silver nitrate. What's the first thing you're going to try and figure out?
What's in it?
What's in it?
What's in it? Okay?
Silver.
We got some silver.
So you got silver nitrate. Silver nitrate soluble?
Get it,
I
get
did.
it.
Better be. Otherwise, you'd be taking it out with a spoon.
Okay.
So, I've got silver nitrate, which means I have what in here?
Silver.
Silver ions.
Silver ions,
Nitrate ions.
nitrate ions, and water. Okay? Now, here's the rule. Nitrate's this big polyatomic ion. It's very complex. Mother Nature is never going to touch the nitrate. Okay? It's too complex. Mother Nature goes, I got easier things to deal with. I am not going to do this. So the only thing that could possibly be reduced or oxidized is silver or water. So when you see something big, dichromate, nitrate, hydroxide, something like that, Mother Nature's not going to mess with it. Okay? It's only going to pick the low-hanging fruit. So, what do you think is going to happen to your Ag plus?
It gains an electron.
Going to gain an electron
Really good.
and turn into
Elemental.
elemental silver. So, does Mother Nature like this option?
Yeah.
Mother Nature likes this option. Now, here's important in terms of the over-under game. Mother Nature could make water go through the reduction process. Okay? But on your chart, Nathan Nelson, silver ions are way up here.
Yeah.
Where is the reduction of water relative to silver?
Under.
Under. So the reduction of water is down here. Right? So which one's Mother Nature going to pick? The upper or the lower?
Upper.
because this is going to be easier. So on the reduction one, Mother Nature will always pick the one that's higher because it wants more favorably to go in that direction. Now, there's one exception to that rule. There's one exception. We really don't know why. It has one theory that it has to do with the electrons. Chlorine is actually like above water. So if you have chloride ions, typically you pick what's below. The one exception to this is chloride. Okay? So on the over-under game, chloride ions are actually above water, and you would think it would pick water before that, but in reality it picks chlorine. So this is why in labs we typically don't use things that involve chlorines for demos, because you're going to generate chlorine gas, which is kind of poisonous. So it's like, what happened? AP physics class, kill chlorine poisoning. Okay. So Mother Nature is going to pick this. Okay? Cool. Now, what's your oxidation things? What's the two things that you can oxidize?
Water.
Water and silver. You could make Ag plus oxidize. But what would you make? You'd make Ag and an electron. Ever see Ag2 plus? No. So, here's what I'm going to do. So I've got my silver nitrate. Take the handy dandy electrodes and kind of flip this over. So we'll do this. So what you'll see.
What is that?
Yucky, what is that?
Okay. So what's on here?
Metal.
Which metal?
Silver.
Yeah.
The only one.
So we just produced
A
your
silver
metal,
form.
your silver.
Is this?
Well, it needs to be.
Yeah.
Don't get touchy. Okay. It's kind of ugly. Wow. Okay. But so what's happening is that the silver is your silver ions. They are more than willing to take in electrons. They're going to take over those electrons, and you're going to make elemental silver. Now, here's the last culminating idea. What?
Go ahead.
Oh, is this how you afford the labs? By making silver?
Yeah. That's
Okay, thank you.
That's it. So,
Report
last one, magnesium nitrate. So if you understand this one, hey,
No,
we're
last one was the
golden.
last one.
So I got magnesium nitrate, which means you have what?
Magnesium. and
Take it away, Cole.
Magnesium nitrate and
Water.
Water.
okay. So this is kind of a cool situation. So you got magnesium ions, you got nitrate ions, and you have water. Which one is Mother Nature not going to touch?
Nitrate.
Nitrate. Don't even worry about that. So we're going to play the over-under game. You don't have to worry about the nitrate. So on the reduction side, okay, on the reduction side, could magnesium take in 2 electrons and make elemental magnesium?
Okay.
Could. Well, where's that out on the reduction chart?
At the very bottom.
Way, 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 way down there. This is big negative value, right?
Probably no point.
Probably no bueno. But on the reduction of water, okay, on the reduction of water, that's farther up, right? So water is going to be the preferred one because that's easier to reduce. So the reduction is not going to be the magnesium. The reduction is going to be the water. Now, on the oxidation, nitrate?
Mm-mm.
Not happening. What about the magnesium? Are you going to take Mg2 plus and turn it into Mg3 plus and an electron?
Never seen that?
Nope. So what's going to get oxidized? Water. So in this situation, water gets both reduced and oxidized. Okay? But when it gets reduced and oxidized, the only thing you're left with is this. So if water is both reduced and oxidized, when you do the half reactions, when the smoke clears, you're just going to make hydrogen and oxygen. Okay? So if water is both reduced and oxidized, Mother Nature says, hey, I'm just going to make water. So if I do this, and it works, we'll add a little phenolphthalein. There we go. Go.
So is that the same as if you just didn't add magnesium nitrate?
Yep. I mean, they're there.
They're spicked.
There.
You're too strong. Whoa.
Whoa.
Yeah,
Whoa.
see?
Whoa.
Oh. That was actually working. So on that side that's turning magenta, what do you got?
OH.
You're producing hydroxide. On the other side, you're making
Hydrogen gas.
hydrogen gas. Now, here's the story. On the one that's making the hydroxide, there's two ways you know that this is the reduction. That was also the largest number of bubbles. That was the most, because you're making 2 moles of hydrogen. You also know that you're making hydroxide ions because it's turning basic. That's why that side turned magenta. This side over here, if we had like a universal indicator, we would see that was turning acidic because you're making hydronium ions and oxygen. This is a big. Okay, let's go back. Top down the camera.